Welcome back, everyone. Before the break, we had started to talk about the role of a scale factor on a rectangle, as well as the role of a scale factor on the surface area and volume of a rectangular prism. In this part of the lesson, we're going to look at the role of a scale factor with some other polyhedrons. Let's go to the board. So guys, in this segment, I'm going to remind you that a scale factor is a number that I multiply any of my dimensions by with regards to a shape. I'm also quickly going to remind you what a polyhedron is. Then we're going to go into scale factors affecting cylinders as well as scale factors affecting spheres and cones. Great. So just a reminder, a polyhedron is a three-dimensional figure with 4 or more flat surfaces. Great. Now let's have a look at the surface area and volume of a cylinder. This is just a reminder of formulas that you have done in the past. Surface area, we add together the exterior shapes that make up the three-dimensional shape. So I'm going to add the area of the two circles, which we know are pi r squared, because that is the area of a circle. So the area of the two circles will give me 2 pi r squared. Then we're going to take the area of the rectangle that wraps around the cylinder, and that area is 2 pi r times h. So just a reminder that that is the surface area of a cylinder. The volume of a cylinder is the area of the base, and the base is a circle. So it's pi r squared, and this is multiplied by my perpendicular height. So the volume of a cylinder is pi r squared times height. So I'm going to ask you to predict what will happen to the surface area of a cylinder if the radius and the height are both multiplied by a scale factor of k. So everyone, for this particular example, I'm going to ask what you think would happen if I multiplied the height as well as the radius by a scale factor of k. What do you think would happen? Let's go to the board. So if the radius and the height are multiplied by a scale factor of k, then my new radius will be kr because it's k times r, and my new height will be kh. So I'm now going to substitute kr in place for my radius and kh in place for my height. So I'm going to have 2 pi times my radius squared, and my new radius is kr, so it's going to be kr squared, plus 2 pi times my new radius, which is kr, and my new height is kh. So if I simplify this, it's going to be 2 pi k squared r squared plus 2 pi k squared r h. So all that I've done is simplify, but is there a way that I can express the new surface area in terms of the old surface area? Is there a connection between this line and this line? I'm going to give you a second to see if there's a way I can express the new in terms of the old. Hopefully, everyone can see that I can take out a highest common factor of k squared because I have a k squared present in both cases. So it's going to be k squared times 2 pi r squared plus 2 pi r h. So guys, for a cylinder, when I increase the height and the radius by a scale factor of k, this affects the surface area of the cylinder. The new cylinder volume will be k squared times the old cylinder surface area. So the new surface area is going to be k squared times the old surface area. Great, let's go to the board. So now that we've seen what happens with the surface area, we are going to predict what will happen to the volume of a cylinder if the radius and the height are multiplied by a scale factor of k. So I'm going to ask everyone to think. If I calculate the volume normally, what will the difference be if I now multiply the height and the radius by a scale factor of k? How is that going to affect my volume? Cool. Let's see if any of your ideas are proved correct. So, because I've multiplied by a scale factor of k, my new radius is kr and my new height is kh. Just a reminder that the volume of a cylinder is equal to pi r squared, which is the area of the bottom circle, multiplied by the height. So the area of the bottom circle multiplied by the perpendicular height. But I now have new expressions for my new radius and my new height, and those are kr and kh. So all I've done is replace my radius with kr, and I've replaced my height with kh. So my new volume will be pi k squared r squared times kh. And if I simplify that one line further, it's going to be pi k cubed r squared h. Now everyone, I'm going to ask you, is there a link between my old volume and my new volume using the fact that I've multiplied by a scale factor of k? Is there a link? Okay. Also, one way to see what the link is to maybe see what the difference is. So the initial volume is pi r squared times the height, but this one is pi k cubed r squared times the height. So we now have a k cubed present. And if I take this out as the highest common factor, it's going to be k cubed times pi r squared h. So I can see that the influence of the scale factor multiplied the new volume to be an expression as the old volume multiplied by k cubed. So guys, in general, if the radius of the circular base and the height of a cylinder have been multiplied by a scale factor of k, then I can generalize that the surface area will be multiplied by k squared and that the volume will be multiplied by k cubed. Great, guys. I hope that everyone's with me. We're going to move on to the next slide. So we're now going to look at the surface area and the volume of a sphere. Just a reminder that the surface area is 4 pi r squared and the volume is 4 over 3 pi r cubed. So I'm going to ask you, what do you think would happen to the surface area and the volume of a sphere if the radius is multiplied by a scale factor of k? So knowing that my surface area of my cylinder was affected as it was multiplied by k squared, and the volume of my cylinder changed as it was multiplied by k cubed, do you think there could possibly be a link between how a scale factor affects the surface area of a three-dimensional figure and the volume of a three-dimensional figure? Is there any connection between what k does to the surface area and the volume? I'm hoping that your brain is getting some ideas. Let's go to the board to see what happens. So we are going to test our predictions for a scale factor of 2 and a scale factor of 4. So if you think that there is going to be a similarity, that means that my surface area is going to be multiplied by k squared. So if there's going to be any kind of connection, we're going to see if my new surface area is multiplied by k squared. So my scale factor is 2, so it would be 4 times it. And for volume, we want to see if my k factor is going to have an effect on it. And that would be k cubed. Great, guys. So we are now going to test to see if we are right. So previously, the new surface area was affected where the new surface area was k squared times the surface area, where k is the scale factor. So I want to see if my new surface area is going to be my scale factor squared, which is 4, times the original surface area, which is 4 pi r squared. So I want to see if my theory is going to be correct if my scale factor squared times the new surface area is the actual new surface area. Then I'm going to test my theory to see if my scale factor cubed multiplied by the original volume is the new volume. So 2 cubed is 8. So we're going to see if my new volume is equal to 8 times my old volume. Similarly, I'm going to see if my scale factor squared, so 4 squared is 16, multiplied by my old surface area is equal to my new surface area. I'm also going to investigate to see whether my scale factor cubed, and in this case it will be 64 because 4 cubed is 64, being multiplied by my volume is representative of my new volume. So everyone, we've now hypothesized about what we think the new volume will be and what the new surface area will be. In the next slide, I've actually shown you the calculations so we can see if our theory is correct. Let's go back to the board. So now for the scale factors, I have actually written that the new r is 2r because I've multiplied it by a scale factor of 2. And if I substitute it into the formula, I can see that it becomes 4 pi times 4 times r squared, which is just 4 times my original surface area. So my theory was correct. It is my scale factor squared times the old surface area to get the new surface area. With the volume, we can see that it actually was true, that by substituting in 2r is my new radius, my new volume is 8 times my old volume. So again, the scale factor cubed times the old volume is the new volume. The exact same thing happened when my scale factor was 4. I have my scale factor squared times my old surface area to get my new surface area. And then similarly, I've got my scale factor cubed that represents my new volume because the scale factor cubed times the old volume is the new volume. So let's go to the next slide. In general, if the radius of the sphere has been multiplied by a scale factor of k, then the surface area will be multiplied by k squared and the volume will be multiplied by k cubed. Let's move on to the next slide. The surface area and volume of a cone. So initially what's going to happen is I'm just going to remind you of the formulas. The volume of a cone is 1/3 pi r squared times height, and the surface area of a cone is pi r length plus pi r squared. So we are now going to predict what happens to the volume of the cone if the radius and the height are multiplied by a scale factor of k. So everyone, previously we know what happened with the scale factor of k with regards to volume. Often it was the case that the new volume was the scale factor cubed times the old volume. So I'm going to see if it happens again. Let's go back to the board. So our prediction is that the new volume of the cone will be k cubed times the old volume, which is 1/3 pi r squared h. Great, everyone. So we've hypothesized that the volume of a cone will be multiplied by k cubed. The next part of this actual lesson, we're going to see what happens to the surface area when I multiply each of my dimensions by a scale factor of k. We're going to see if it's the same thing or if there are any differences. But we'll do that straight after the break.